Hi, I'm Jawad. Welcome. In this short presentation, we'll explore distributed databases, what they are, why they matter, and how they work. A distributed database stores data across multiple networked computers, but appears to users as a single logical database. Organizations use distributed databases to improve availability, scale horizontally, and keep data close to users around the world. Over the next slides, I'll walk you through architecture, fragmentation and replication strategies, consistency models like cap and base, query processing, distributed transactions, recovery, and real-world use cases. By the end, you'll understand key trade-offs and practical considerations when designing or choosing a distributed database system.
This slide lays out the roadmap for our discussion. First, we'll establish the core definition and motivations for distributed databases. Next, we'll examine architectural building blocks and the roles of nodes, metadata managers, and transaction coordinators. Then we'll look closely at data distribution, fragmentation, replication, and allocation tactics. We'll follow with consistency models, highlighting cap trade-offs and base alternatives. After that, we'll discuss query processing and optimization across nodes, and then distributed transactions and commit protocols. We'll cover concurrency control, recovery strategies, and security privacy concerns. Finally, we'll survey real-world use cases and weigh advantages against operational costs. Treat this map as a checklist as we move through each topic.
A distributed database is a logically unified collection of data physically spread across multiple servers or data centers. The system hides the distribution from users, presenting a single coherent view of the data. Main goals include increased availability, fault tolerance, and reduced latency through locality. By distributing data, systems scale horizontally, adding nodes to handle more load, and can place data near users to speed reads. But distribution also adds complexity. Consistent updates across nodes, network partitions, and partial failures require careful design choices. Trade-offs between consistency, availability, and latency are central. Knowing the application's SLAs, access patterns, and failure model helps choose an appropriate distributed architecture. Typical distributed database architectures include several core components. Individual nodes store data and execute local queries. A network layer enables inter-node communication, often via RPC or message passing. A metadata manager or global directory tracks where fragments and replicas reside and routes queries. Transaction managers coordinate multi-node operations to maintain desired consistency. Query processors decompose global queries into efficient local subqueries and reconstruct results. Replication managers ensure copies are propagated and reconciled. Monitoring, failure detectors, and leader election or consensus services like those used for metadata are often part of the control plane. Evaluating a system means asking how each component scales and how failures in one layer affect the whole. Distributed databases appear in different forms. Homogeneous systems run the same DBMS software across all nodes, simplifying schema management, replication, and query planning. Heterogeneous systems integrate different DBMS products, which is useful when merging legacy systems or across organizational boundaries. They typically require middleware or a federation layer. Federated DBMS architectures let autonomous databases collaborate while preserving local control and policies. Each type involves trade-offs. Homogeneous deployments are operationally simpler and easier to optimize, while heterogeneous and federated setups offer flexibility and incremental integration at the cost of more complex query translation and metadata mapping. Data distribution is organized around three complementary strategies: fragmentation, replication, and allocation. Fragmentation splits relations into fragments. Horizontal fragments divide rows, vertical fragments split attributes, and hybrids combine both. Replication copies data across nodes to boost availability and read throughput. Allocation determines where fragments and replicas are placed, based on workload patterns, latency targets, storage constraints, and regulatory requirements. The right distribution balances locality, reducing cross-node transfers, redundancy. Fragmentation improves performance by partitioning large relations into smaller pieces. Horizontal fragmentation stores subsets of rows, often by region or tenant, so queries touching local data avoid cross-node traffic. Vertical fragmentation splits columns across nodes. Joins on a common primary key reassemble the logical tuples. Hybrid fragmentation mixes both approaches for complex workloads. A crucial property is reconstructibility. Fragments must recombine into the original relation via unions or joins. While fragmentation reduces data transfer for many queries, it complicates global joins and query planning. Optimizers must plan operations to minimize expensive cross-node data movement. Replication increases availability and read performance by keeping multiple copies of data. Primary, secondary, master-slave models designate a single writable primary and replicate changes to read-only secondaries. Simple to implement, but write-limited. Multi-primary, multi-master setups allow concurrent writes on multiple nodes to scale writes but require conflict detection and reconciliation. Replication can be synchronous, ensuring strong consistency at higher latencies, or asynchronous, improving performance but permitting temporary divergences. The chosen replication approach shapes write latency, recovery procedures after failures, and the complexity of conflict resolution logic during reconciliation. Sharding is horizontal partitioning that distributes data across nodes using a shard key. Range partitioning assigns contiguous key ranges to shards. Hash partitioning distributes entries via a hash function to achieve uniform load, and list partitioning maps specific values to shards. Good shard key selection balances load while preserving locality for frequent queries. A poor choice creates hotspots. Rebalancing, moving shards when nodes change, is operationally complex and must preserve availability. Monitoring tools and automated resharding help maintain even distribution. For many large-scale systems, sharding is essential to fit datasets across many machines and to scale throughput. CAP theorem states that during network partitions, a distributed system must choose between consistency and availability. Because partitions can and do occur, practical systems trade off consistency for availability, or vice versa. Strong consistency models like linearizability provide intuitive semantics but can increase latency or reduce availability. Eventual consistency favors availability and performance but allows temporary divergence until replicas converge. There are intermediate models, causal and session consistency, that offer useful guarantees without full strong consistency. Basically available, soft state, eventual consistency, contrasts with ACID and suits many geo-distributed systems, prioritizing responsiveness over immediate consistency. Distributed query processing decomposes a global query into local subqueries executed across nodes. The global query processor handles decomposition, localization, and result reconstruction. Optimizers must consider CPU and I/O costs, as well as network transfer and latency. So they push predicates to where data resides and avoid unnecessary data movement. Techniques include shipping queries to data, shipping partial results, using Bloom filters to reduce join traffic, and replicated joins to leverage local copies. Cost-based planners require accurate distribution statistics and network models. Efficient distributed planning is essential to keep multi-node queries performant and predictable. Distributed transactions preserve ACID semantics across nodes when needed. Two-phase commit, 2PC, coordinates prepare and commit phases where participants vote before committing. It ensures atomic commits, but is a blocking protocol susceptible to coordinator failures. Three-phase commit reduces blocking, but adds complexity. Consensus protocols such as Paxos and Raft are often used for fault-tolerant coordination services, leader election, and metadata management. To reduce cross-node locking, many architectures prefer per-shard transactions, optimistic concurrency, or saga patterns for long-running workflows. The transaction model chosen affects latency, throughput, and system complexity. Cancellation control options include distributed locking, timestamp ordering, and optimistic concurrency control. Locking enforces strict isolation but can introduce contention and deadlocks. Timestamp or optimistic methods reduce locking at the cost of retries and conflict resolution. For recovery, write-ahead logging, checkpoints, and replica synchronization are common. After node failure, replicas catch up via log replay or state transfer. Different failure models, crash failures, network partitions, and Byzantine faults, demand different strategies. Designing for fast, deterministic recovery and clear failure semantics is crucial to preserving availability and predictable behavior after outages. Security and privacy are critical in distributed environments. Use federated or centralized authentication and consistent authorization policies across nodes.
Protect data in transit with TLS, and encrypt sensitive data at rest to minimize risk from compromised storage. Maintain comprehensive auditing and logging for compliance and incident response. Apply fine-grained access control and data masking to meet regulatory requirements. When data spans jurisdictions, privacy laws like GDPR may restrict where personal data can be stored, requiring careful placement and anonymization strategies. Building security into placement and replication decisions reduces legal and operational risks.
Distributed databases excel in global applications, large-scale analytics, IoT backends, and social platforms needing scale, low latency, and high availability. Advantages include horizontal scalability, resilience to localized failures, and improved data locality. Drawbacks include increased system complexity, operational overhead, and trade-offs around consistency. When choosing a system, map your workload to the architecture. Choose strong consistency for financial or safety-critical systems, and favor eventual consistency for highly available, read-heavy services. Monitor, automate rebalancing, and design clear failure semantics to keep operations manageable. Thank you. Feel free to ask for the version with these lines added into the PowerPoint notes or converted into TTS files.